Uh, our final speaker is George Sklivanitis. He's a research assistant professor of electrical engineering and computer science, a faculty fellow with the Institute for Sensing and Embedded Network Systems Engineering, ISENS, and a founding member of the Center for Connected Autonomy and Artificial Intelligence at FAU. Prior to joining FAU, Dr. Sklivanitis received his PhD degree in electrical engineering from the University of Buffalo in 2018. His research focuses on modeling, optimization, and experimental evaluation of autonomous networked AI systems in challenging, congested, and sometimes contested communication environments, such as underwater, in the sky, and in space. He has a number of awards. He ranked first among all U.S. universities in the NUTAC Software-Defined Radio Academic U.S. National Contest in 2014, and was recognized by The Economist as one of 3 winners of the World Ocean Initiative's Ocean Changemakers Challenge in 2021. He's also a co-founder of the IEEE Workshop on Wireless Communications and Networking in Extreme Environments, which started in 2017. So with that said, welcome, George. I'm happy to see you.
Thank you, Nick. Happy to see you too.
Thank you. And you can take the floor.
Thank you. Thank you, Nick, and thank you to everybody that is staying so late in a Friday evening. I'm excited to close this wonderful day of presentations.
Yeah, we can see everything.
You can see everything? Great. So today I will be talking about work that we have been doing at the Center for Connected Autonomy and AI on Agile Waveform design for always-on wireless connectivity in challenging environments. This is joint work with Amir Torabi and Dr. Dimitris Pados from the center. But before I jump into the main part of my presentation, let me first acknowledge all the supporters of the center, as well as the center itself, which started actually operating on March 2021 as part of the College of Engineering and Computer Science. We are currently counting 8 faculty senior members and about 20 students working in the center. We are located at the Boca Raton campus of Florida Atlantic University. And here is what we believe can really create the future of networked artificial intelligence and connected autonomous systems that are either swimming underwater or they are moving in the ground or flying in the air or in the space. So we see this as three main components, and one of these components is actually going to be the main piece of my talk today. First, we need autonomous, resilient communications between the machines that we are connecting, the agents that we are connecting. Second, we need to train robustly these multi AI agents, and finally, we need to be able to monitor in real time that they are operating as they should, right? So here is just a few pictures that are depicting the number of autonomous systems that we are working with at the center, and as you see, they are spanning all these 3 different environments. So with that, let me jump into the main part of the talk today, which is about how do we establish reliable and resilient machine-to-machine communications, right? Conventional resource utilization, as we all know, over time and frequency today, is offering limited flexibility, especially in contested or congested environments, right? Our spectrum, especially below 6 gigahertz, is highly congested. Moving to new frequencies can certainly give us opportunities, but this comes with huge responsibilities as well. So not to interfere with existing incumbents, right? So teams of future human or human/AI agents that will be deployed in the ground, in the air or space, will have to deal with dynamically changing conditions, widely varying mobility, and changing network topologies. What we believe is required naturally is for enabling agile, robust internetworking of all these assets is to treat jointly all these available space-time and frequency resources, right? So instead of looking for white spaces or bands that might be unused and you could use some part of the time, we propose actually to listen and sense the entire available spectrum, use one or more pulses that you could use to carry your information, symbols on top of that frequencies, and do that in a repeated fashion, right? So use this, repeatedly optimize these waveforms to try to accommodate for dynamic mission demands or even dynamic and dynamically varying link and network dynamics. Some background on the fundamentals behind the waveform design for people that might not be familiar with. This is out of your digital communications textbook. So this is your waveform that will eventually be transmitted and carry your symbols over your channel. And there are three main components that consist that waveform, right? So what are you transmitting? The symbols. How to transmit the symbols. Usually this is a basic pulse shaping filter. And where to transmit these symbols in time and space, which is represented by this lattice, right? Our proposal is using as P of T that you see in this slide here as your pulse shaping filter, a coded series of pulses, psi of T with the notation that we have here, of duration T sub C. These pulses can be coded, we can use repetitions, coded repetitions of these pulses using this code S sub L, and specifically here S sub L is taking values from a finite alphabet alpha. And now by optimizing the number of repetitions of this code optimized pulses psi of T, we can uniquely trade off the data rate that we will be achieving versus the interference avoidance, right? So more repetitions would offer us more resilience to potential interference. Less repetitions will boost our data rate, right? So getting into the core part of how do we design now these waveforms, we formulate this following optimization problem, which is saying that we want to maximize the maximum attainable SINR at the output of the receiver that we want to communicate with, right? So imagine that you have your transceiver pair. This transceiver pair now, this transmitter is using transmitter energy per bit denoted by E here, and S is that vector containing the number and the alphabet of the coded optimized pulses that I showed you before. And now you're looking to find this optimal pair of energy and code that would maximize this quadratic expression here, which is actually a closed form expression of your signal to interference plus noise ratio, right? H here models specifically your multipath channel matrix. R hat is an estimate of the locally sensed disturbance that your receiver experiences. And Emax here is your maximum available allowable bit energy. Right, so all you would need to do in a network of these transceivers would be to periodically compute over time this optimal pair at a rate that satisfies the channel coherence time, and at every hop of your multi-hop ad hoc network, you could feed back now this optimal pair to the corresponding transmitter to avoid potential interference. Now, if that code that you're looking for is actually taking values over the complex alphabet, then the solution to the optimal solution to this problem is actually the principal eigenvector of this channel processed disturbance matrix that you see here in the middle. So it's pretty simple to calculate. However, we are working with digital signals, so the code that you will need to be using will be taking values from a discrete alphabet. in this example here, we assume that the code actually takes values from the binary antipodal alphabet. And one potential way to calculate your optimal waveform would be to exhaustively search for this binary code that would be maximizing now your SINR, right? So here are some simulation studies that we have carried over in the past, and there are actually multiple algorithms that our group has developed over the years in order to solve this problem close to optimally with lower complexity, right? So on the right-hand side, on the y-axis, you see the SINR loss that you would have because now you're using codes from the discrete alphabet, the discrete binary alphabet, and not from the complex alphabet. We assume here that your code has 16 chips. We consider a link of interest that's operating at 10 dB, and we consider a varying number of code channel users that are operating at the same frequency and at the same time with our link of interest that can take values between 8 and 11 dB. With green here, you see what would happen if you would hardly quantize the principal eigenvector of that channel process disturbance matrix, and with purple, actually, you see an adaptive binary optimized solution to the same problem. And finally, with red color and blue, overlapping with that blue color, you see the proposed algorithm that we have developed, which is based on single bit flipping for calculation of that optimal code, and actually shows that it matches in terms of SINR performance the performance of the exhaustive solution. But let's move on to actually experimental evaluation of this concept over a software-defined radio testbed. This is results that we got by setting up two links. With the blue line here, you see a link between two USRPs that are establishing a communication link, a non-adaptive communication link. And with red, you see again another link that now adapts based on the locally sensed interference at the receiver, right? What I want you to keep from this slide, actually, on the two plots on the right-hand side, where we plot pre-detection SINR at the receiver, so the SINR that you will be using to extract your bits at the end, versus time, is that in the plot on the left, we compare the performance, the SINR performance of our adaptive link, of our red link, when the blue link is actually a narrowband BPSK link, right? So the performance improvement that we are getting once the red link now adapts is about 8 dB for that link. And at the same time, the exciting improvement that we are getting for the blue link, the non-adaptive link, is that we managed to allow to improve its performance by almost 18 dB without, though, doing any changes whatsoever in the communication parameters of the blue link, right? So the only thing that we change is the code that the red link is using, and that frees up space that now can be used by the blue link. Now, in the case that the blue link is a wideband user, it's a spread spectrum user, the improvements are there are still improvements, but of course they are smaller. So we get about 3 dB performance improvement for the blue link, again without changing any parameters. The blue link is a static link, and we get the same 8 dB of performance improvements in SNR for our red link. Now, this was an implementation that was based on software-defined radios where most of the processing has been taking place on the processor. So we were constrained in terms of the link throughput at about 800 kilobits per second. And these experiments took place at Wi-Fi frequencies, and we used coded repetitions of 15 square root rate cosine pulses. Now, for the rest of the presentation today, actually, we'll spend some time to talk about latest work that we have been doing on transitioning most of the algorithmic developments to a system on a chip. And why is that, right? This is because new system on a chip platforms like the Xilinx Zinc platform, which we are using for our experiments in this work, are actually interfacing now a programmable system in the same chipset with a programmable logic system, right? So you could use a programmable logic for high-speed parallel deterministic processing when that's needed, and you could use the programming system for sequential or unpredictable processing. The Zinc architecture is, as I said, featuring both these systems under the same chip, and provides a low latency and high bandwidth link interface between them. So now you could split some of these processing functionalities between the two devices without losing in terms of performance. So the hardware that we have been using for this work is based on the Zinc UltraScale family of multiprocessing system on a chip. These are some of the characteristics here of the platform that we're using. Specifically, this is the ZCU102 evaluation board by Xilinx. We have interfaced this computing platform with a radio chipset from Analog Devices. This is the blue board that you see on the top. This radio frequency transceiver actually consists of 2 transmit and 2 receive chains. It has a wide tuning range from 70 megahertz up to 6 gigahertz. It has also a bandwidth up to 56 megahertz. The ADCs and DACs are at 640 and 320 megasamples per second. And here are also some other characteristics with respect to transmit gain and noise figure for the boards. This is the workflow that we have been following for transitioning most of our algorithmic developments from the processor to the FPGA. So we started using MATLAB and Simulink in particular to simulate our algorithms. The next step was using HDL coder, which allows us to translate most of our Simulink code to hardware description language. Then this hardware description language is, of course, undergoing synthesis, fitting, and timing analysis. Of course, in some cases, if the output of this analysis there are errors, we go back to the simulation in Simulink, and then we repeat that process over and over again until we are able to target and fit our design in the FPGA hardware. So this is sort of depicting the process and the tools and the software tools that we have been using to deploy our algorithms in that system on a chip platform. Here is a brief overview of how the Simulink model that we are actually implementing in the FPGA is looking like. So on the top, you see the different transmitter blocks, which correspond of a bunch of blocks that have to do with packetization and symbol mapping, pilot insertion, channel modulation, where our channelization codes are actually used to map our symbols to chips, and then also formulate these waveforms. And on the bottom side, you see the different blocks of our receiver, which consist of timing acquisition algorithms, frequency synchronization, frame detection, channel equalization, symbol demapping, as well as SINR and bit error rate calculation. And most importantly, the waveform optimization block, which actually I will talk about in this slide. So for calculating our optimized waveforms, what we are doing is that we are estimating our local disturbance by sample averaging samples of disturbance when our transmitter is not on. And then in this particular design, we are calculating that optimal waveform by exhaustively searching through all the 2 to the L code waveforms that are minimizing now this quantity down here. This is also this block design here depicts all the blocks that we have used for our Simulink simulation and for our FPGA implementation. This is a picture of our software-defined testbed in the lab. In the middle, you see the system on a chip platform. We are using just one single TX and one single RX antenna for this setup. On the left side, you see an interferer, which is a USRP, B210 in this case. Now, on the right-hand side, you see the packet formatting that we have used for this link for this experiment. We have, as you see, a preamble sequence, which is a Golay sequence that's used for automatic gain control and frame acquisition at the receiver. We have a training sequence of 128 symbols that's used for timing synchronization and carrier frequency offset estimation and compensation at the receiver. And finally, our physical layer data frame, which has a configurable size. On the back of this image, actually, you see on the left of this screen, you see how the constellation looks like. So in this particular experiment, we have been demonstrating 64 QAM. And on the right-hand side of this image, you see actually the different levels of SINR, where actually I will analyze later on in our presentation. These are some of the parameters of the testbed. We used waveforms that have different length so that we can test that trade-off between data rate and interference avoidance. We consider 64 QAM as our modulation scheme. We selected 2.485 GHz as our center frequency. We selected 4 different bandwidths, which resulted in 2 different link throughputs of 5 and 10 megabits per second. We have 4 different bandwidths for our interferer and 2 different power levels for our interferer. Let me get into the results. So these are actually live recordings of pre-detection SINR, similar to what you've seen in the previous software-defined testbed. The difference here is that we have links of much bigger bandwidth and much bigger data rate. On the left, you see experiments that we've done for link bandwidth of 9 megahertz and codes of length 8. With red lines, you see recordings when the power of the signal over the interferer is minus 10 dB, and with blue, you see what happens when the power of the signal over the interferer is minus 20 dB. On the right-hand side, you see the same idea for different link bandwidths and different code lengths. What I want you to keep from this slide is that for the first 1,000 packets, we consider normal operation. So this link is operating by itself without an interferer being on, right? Then at packet 1,000 number 1, we turn on the interferer, and we do not do any type of adaptation. We do not run our optimization algorithm at the receiver side. And here you see the performance degradation of our link, which in some cases can go all the way from 28 down to 12, 13 dB, right? Now at packet number 2000, we turn on that switch of adaptation, and now our main link starts dynamically estimating the disturbance and calculating an optimized code, which will send back to the transmitter so that the transmitter can use that to avoid interference. And you see that in some cases, we can fully restore SINR performance. And in some other cases, we can actually bring back our link from being completely dead. And actually, this can be seen by these following constellation plots, which show these three different stages much more clearly. So on the left side, you see how the constellation looks like specifically for code length of 8. On the middle, you see what happens when our interferer turns on. And on the last plot, you see what happens when our link starts adapting to that interference. On the bottom, you see the same series of events. The only difference is that the code length here is bigger. So we can still withstand some interference even if we are not adapting our link. Although, as you see, I mean, this is certainly a very noisy constellation. And once we adapt the link, of course, we will be getting a much cleaner constellation, right? So that's what I want you to keep from these experiments. Again, the second set of results I have demonstrate performance for 18 megahertz and 27 megahertz, where we get much higher bit rates of 10 megabits per second in this case, and we can withstand interference better because actually our interferers are constrained. The maximum bandwidth of our interferer is constrained by the Ethernet bottleneck of the USRP, which allows us to operate it only at 2.4 megahertz. That's another real live recording of the adaptation of our link directly from our oscilloscope. On the left-hand side, with orange color, you see the 15 megahertz spectrum of our link, and with white color, you see actually the bandwidth of the recorded bandwidth of our code channel interferer, which is operating at the same center frequency. On the right-hand side, you see what happens when actually we turn that switch of adaptation on. So you see that automatically the shape of our link is bending around the main lobe of the energy that is carried by our interferer, so that it can avoid it. Right? So in conclusion, we demonstrated real-time high-throughput interference avoidance for the first time by exploiting the high-level parallelism of FPGAs. We demonstrated trade-off between data rate and interference avoidance by tuning dynamically the number of code repetitions. We've shown that optimal waveforms can be designed actually in less than a couple of milliseconds to prevent link disruption by interferes. Narrowband or wideband code channel interference can be sensed and characterized across the entire spectrum of our radios. And finally, we have achieved 10 megabits per second links to support data demanding applications for network AI, such as an example of video streaming would be a good example, right? So with that, we can open the floor for questions, I guess, if there are any. Thanks very much again for inviting me for this presentation. And Nick, back to you.
Thank you very much, George. That's an excellent presentation. Anyone have any questions? It's really nice to see this evolve from where it started to where it is now. I think this is the first time I'm seeing these really very nicely presented results and figures illustrating exactly what's happening. I think that's quite impressive.
Thank you, Nick. Thanks.
Any questions from the audience? All right. I guess my only question, I know we're pushing time here, is you show that very nice FPGA design flow graph.
Yeah.
I guess now what's the most challenging part then of working with the programmable logic? Obviously, there's many steps here.
Right. I believe that the thing that takes the most time is really the synthesis, fitting, and timing analysis, and this loop back to your design, back to Simulink, and back to the logic of the algorithm that you are simulating. So this can certainly take a lot of time because synthesis times for producing hardware code can certainly take a lot of time. So if we compare, this workflow with the workflow that you would follow with, let's say, programming your algorithms in GNU Radio, running them in a processor, this is certainly something much more time-consuming, both for debugging and operation. So it's definitely tedious, but at the same time, it saves a lot of time because these high-level synthesis tools that allows you to go directly from MATLAB or Simulink code to hardware code can save you a lot of training time, especially for students or new researchers that cannot go directly and write their own VHDL or Verilog blocks.
All right, great. Yeah, any last questions here? Otherwise, we can conclude the session and the event, I suppose. Yep.
Thank you, Nick. Thanks.
Thank you very much. I've lost my, well, anyway, 1 second. So it appears that I've lost the main page, but this is time for the closing remarks. So yeah, that concludes the final session of the event and the third Buffalo Day for 5G and wireless Internet of Things. There are really a lot of people to thank for this successful day. We started, thank you to Dean Lewis for kicking off the event. Thank you to all of the keynote speakers, the panelists, the presentations, all the students who prepared posters and demos for the event. Of course, thank you all to the organizing committee and especially to our partners at FAU for helping us, and to Professor Zhonghu, who's really worked tirelessly to bring everyone together here today and get all these speakers together. And finally, thank you, of course, to all the attendees who joined. Without you, we wouldn't really have an event. There is an announcement that there will be another event next year in November. It'll be organized with help by a UBEE again, and also UBCMI, and in collaboration with the Ohio State University. If Kevin would like to say anything, be happy to hear from you. Otherwise, that's the end of the event, and we thank you all very much for a great day. It was a long day, but thank you. And we made it with 15 minutes over length. So.
Sure. Hi, Nick. So for some reason, I couldn't see my my own camera. So can you see me?
I could see you, yeah.
Okay. I just couldn't see myself. So, but anyway, yeah, this is a great event. So I'm pretty excited and very honored to be invited to serve as the next chair. So I certainly feel like I have a big shoe to fill next year. So I certainly will learn a lot from you guys, and hopefully I will do a good job next year. And thanks again for inviting me to serve to chair this Buffalo Wireless Day event.
Thank you. Any final words from Zhonghu or anyone else?
I don't have anything to add. Alan, do you want to add anything?
Oh, I'd just like to say thanks for the opportunity. This is a great event. I'm really looking forward to next year.
Thank you. All right then. So I think we can close out. Thank you all again for joining.
Yeah.
It's a great day.
Thanks.
Have a great
And
Friday
also
night.
happy Thanksgiving. Yeah.
Bye.
Bye.